In quantum mechanics, particles are things we only see when we measure them, but how they move around is described by a wave function that satisfies the Schrödinger equation, which I talked about in my last video. But what is a wave function? Let's take a look. Here's an example of a wave function. These two are mathematically equivalent, although this one's easier to do calculations with. But we'll use this form for this video as it's easier to visualize. This wave function depends on time and one dimension of space, which is a simplification from a real particle which exists in 3 dimensions of space, but this simplification allows us to plot this function. So let's do that. We'll just plot the first part of this wave function to begin with. This is simply a cosine wave. Note that the k is a variable controlling the size of the wavelength, the omega controls the oscillation frequency, and the prefactor a controls the amplitude. So different parameters will make different waves. Now, to plot the second part of the wave, we're going to need another axis, even though the wave is one-dimensional. This is because the sine part of the wave function is multiplied by the imaginary number I, making it a complex wave function. So here they are, both plotted independently, but if we plot the whole thing together, we get this, a spiral of complex values, which would go from -infinity to +infinity, but I'm just plotting a section of it here. This is fixed at one point in time, but if we turn time on, we get an oscillation, which in this case manifests as a winding of the spiral. So that's what a quantum wave function looks like. But what actually is it? It's called a probability amplitude, and isn't anything physical on its own, but if you take the mod squared of the amplitude, it tells you the probability of finding the particle at any point in this one-dimensional space. So we can extract the position of a particle from this wave function. Actually, the wave function doesn't just tell you about the probability of position, but all other measurable physical quantities like momentum or energy or spin. We just need to do different mathematical operations on the wave function for each one. But overall, the wave function is a mathematical tool which keeps track of all of the properties of a quantum particle and explains our observations of the probabilistic nature of where particles appear when we do experiments on them. I could end there, but there's a really important property of this wave function which you need to know about. In this video, I've drawn the wave function like this, going from -infinity to +infinity. But what about other shapes like this? Well, because the wave function is linear, as in it doesn't have any x squareds or t squareds in it, you can have a valid wave function that's any combination of other wave functions added together, called a linear combination. This means that you can represent a wave function of any shape just by adding together many waves with different parameters, and also represent waves in 3 dimensions instead of 1. This linear combination of wave functions is also important for superposition and entanglement, but these are topics for another day.